the chapter. Today we'll be welcoming and we'll be truly honored to welcome Professor Amlan Chakrabarti to deliver a technical talk on the title Journey into the Quantum Realm, Unveiling the Intricacies of Quantum Machine Learning. To begin with, Professor Amlan Chakrabarti is a prominent academic and research chair specializing in information technology. He serves as the director of the A.K. Choudhury School of Information Technology at University of Calcutta. With over 20 years of experience in engineering, education, and research, his work spans various domains, including machine INSA visiting faculty fellowship. Along with that, he has been recognized with the Shiksha Ratna Award by the Department of Higher Education, Government of West Bengal. He has published over 200 research papers and has graduated 20 PhD students. His contribution to quantum computing, particularly in logic synthesis and quantum algorithms, are notable. He also holds editorial roles in several prestigious journals and is involved with various national and international research projects. So, thank you, sir, for joining with us today and find some spare time to deliver this excellent talk. So, without any further ado, I would request Professor Chakrabarti to share the virtual podium with us. Thank you.
Thank you, Ria, for this brief introduction, and thanks to the IIT Kharagpur, the IEEE Student Branch for hosting me. This student branch is very close to me. Many of the volunteers of IEEE, of this student branch connects me very often, and I'm very happy that this is one of the a very exciting student branch of our country, right? And obviously, IIT Kharagpur being a very prestigious institute, and the students of IIT Kharagpur obviously seems it's a very promising act they're doing. So IEEE, we all are the volunteers of IEEE. So obviously, being a part of this IEEE Greater Society, I want to also address you today, and I wish that this type of programs organized by IEEE chapter, student branch, right? This should be well participated, right? And this should help the students, the researchers at large, to develop their knowledge. So what I will discuss today is obviously one of the very interesting domain, which is quantum machine learning, which is very upcoming too. Quantum computing, though it is not a very very long existing domain, the quantum physics or quantum systems it started from 1900, but quantum computing in the last decade, I can say, right, or in the last 2 decades, have really picked up, right? And due to the National Quantum Mission in India, supported by Department of Science and Technology, and the quantum missions which has been already active in many of the developing countries. Quantum computing and research towards quantum computing at large is obviously a very interesting domain for the researchers in computer science, electrical engineering, physics, mathematical sciences, social sciences, chemistry, right, and design and biology, so this itself obviously pushes us to know that how we can better explore the quantum platform to practice or to implement different types of computation and to solve different types of computation problems. Myself, from the computer science background, I am more oriented towards the computer science problems, but obviously there are a lot of problems which now quantum computer takes care, in the basic sciences also, material sciences also. So without not doing much more on this introduction, let's try to focus on my specific lecture, which is obviously how we can exploit the quantum computing platform, quantum computing platform for for implementing or for planning our machine learning algorithms, on this quantum platform, right? Being a quantum computer researcher or being a very passionate quantum computing researcher, it is not my intention that to push all of you to that, hey, quantum computer is the only platform for machine learning. No, I'm not pushing that to all of you. What I'm trying to push you is that, hey, quantum computing has a lot of things, which we can utilize to develop this machine, to solve the machine learning problems uh, in a better way, in many of the cases compared to the existing classical computing. So that will be my pitch throughout this lecture, that how we can exploit the quantum computing paradigm. So on that line, I hope my slide is visible to all of you, right? Is it
Yes,
visible
sir.
to all?
Yes, sir.
Yes,
Yes,
sir.
it is.
Okay, good.
Yes, sir.
So on that page, I will try to start my lecture. That obviously it's a journey in the quantum realm, right? And trying to look at how we can understand some of the properties or some of the things we can do in the quantum computing domain, and we can extend them, and we can utilize them, we can leverage them, to have better machine learning algorithms, right? And how it can be done, this will be discussed in the entire lecture. So my lecture consists of two sections. The section one is basically on the basics of quantum machine learning, right? The basics of how quantum circuits are employed for machine learning, because it is required, because when I speak on quantum computing, I don't know that where the audience is, because quantum computing have different levels, right? You can be only knowledgeable in the basics of quantum computing. You are not so much knowledgeable in the quantum algorithms, and then onwards. So I try to keep some basic part in my lecture, and then I will straight away take all of you towards the quantum machine learning, and then I will just try to excite you with some of the research work, but it depends on the time. So 1 hour duration. I will try to finish this by 50 minutes, so that we can also have a discussion session after this. So we'll, right, and the last I will finish up with some concept, some challenges. So this is what is our journey of computing systems, right? If we look from the left to right, we find the computing systems which started with this electromechanical relay-based computers, which can only do some sort of number crunching, right? And then the most popular age of silicon age of computing came, where from the discovery of transistors and then design fabrication of silicon chips, which actually gets all of us into an era, at present era, of around 3 nanometer, size, feature size, 1.5 nanometer in the fabrication line, right? And that tells that there's enough miniaturization of the transistor size, and this enough miniaturization of transistor size gives us the opportunity to have billions of transistors, and to have very a very large number of circuits on a single chip, right? And that gives you an enormous power of computation. The amount of computation a smart mobile phone can do nowadays is at least 10 times the computation what we used to do with the standard computer 20 years ago. So this because these particular chips are now more powerful, and we have the era of SoC and chiplets, which means that it is not only a single functional module which gets into a chip, multiple functional modules gets into a chip, and the chip becomes a system. So a small chip now drives the entire large system of computing. So that's the journey we are now into, right? And that is the miniaturization of the transistor sizing. A lot of progress in the material science, VLSI design, and VLSI process technology. But if we go further, at the present point of time, we are already hitting the atomic layer inside the devices, right? Our transistors are only one atomic layer or a few atomic layer depth. Now can we can we take the next leap that, hey, can we do computing, right, using the atomic states itself? Okay, not the bulk atomic states which makes a transistor device, but we define computation on the atomic states itself, right? So atomic states means there can be several ways we can exploit this, right? Atomic states can be the nuclear spin of the atom, right? It can be the electronic charge of the atom, right? It can be the movement of the electrons, right, in the atom. So there's a lot of different types of observables we can think of when we go into the matter of that particular level. And when we hit the matter at that particular level, what we are hitting the quantum regime. So quantum regime means actually matter at that particular level, at the atomic and subatomic levels, are being governed by quantum mechanical properties. Okay, one of the primary thing of quantum mechanical property is the discreteness, right? Though we can say the electron spins, we can say the electron energy, we can say the electron directions, but all these are quantized, which means that there are some definite states, quantized states on which all of these can be measured. Okay, so now this gives us this discreteness in this particular system gives us an opportunity there, that can we define memory out of these systems? Can we define computing? The computing in a very broad sense is nothing but, right, you initialize the system with some memory value, and on the process of computing in the system, you go on updating those memories, right, and ultimately stop to a point where your memory contains the result what is expected by this computing. So basically, any computing system should have a way to store the data and a way to update the data, okay, as per the requirement, and the requirement is defined by the computer program, right? And so if we can do a controlled update of the memory, and we can again take the data out of the memory, right, that particular any way we can form the system defines a computing system. Okay, right? How large, how large amount of data we can store and update, and how fast we can update the data based on the computational logic, that defines the power of the computation. Okay, so obviously, from the miniaturization and hitting the quantum regime, the next level of thought was that, can we do a better data crunching in this particular computing systems, which utilizes the atomic, subatomic states? Can we do faster computation in this regime? Okay, and obviously, these questions have been well answered in the quantum regime, and has been proved in many of the cases can be done. Not all the cases. It's not a thumb rule that all the things will be good in quantum computer. Okay, so but many cases the quantum computer performs better in terms of the larger amount of data space or search space, and it can compute that larger amount of search space in a lesser amount of time compared to the classical computing, and that obviously gives us a push that why not quantum computer. Okay, so so this is what I say that a comparison, head-to-head comparison between the classical computing and quantum computing. Okay, so in the classical computing, what we have the definite states of our logic variables. Okay, the logic variables can be of value 0 and 1, and which are equivalent to the data what we store in the memory corresponding to these variables. But in the case of quantum computers, this particular variables which are called qubits or quantum bits, have a peculiar property that obviously they can store a value of 0 and 1, but they can also represent a value which is a superposition, or which is a vector which has two components, one across the 0 state and one across the 1 state. Okay, the component is again defined by the complex amplitude which it associates with each of these particular states. Okay, and this will be pretty clear when I go to the next discussion, okay, of the quantum state of quantum system. But let us try to assume that this particular quantum bit can not only represent a pure 0 or pure 1, but also can represent a state which is of some fractional value of 0 and fractional value of 1, which means that if we try to measure it, it can collapse on 1 with some value which is not exactly okay, that means the all 1, but it has some probability of getting 1, and similarly it has also some probability of getting to 0. Right? How that it helps? This is a simple thing called superposition. Okay, representing the states simultaneously, and when you involve more number of qubits, okay, the number of states a set of qubits can represent goes exponential, which means that due to the superposition, okay, one qubit can represent two states, some probability of 0, some probability of 1. And if we go with n qubits, the number of state representations will be 2 to the power n. So what it does, it goes in the exascale computing, in the sense that using a lesser amount of qubit resource, you can represent a very large amount of data space. And that is where we lead to exascale computing in quantum domain, okay? And this enhances the computing capacity. Not only we can represent the data in the superposition form, and we can represent a larger sort space, a larger data space using a smaller number of qubits. Also the quantum functions or the quantum operations can simultaneously work on all of those data points, all of those states at one shot. Okay, so that gives you a sort of parallelism, which actually leads to a huge amount of the reduction in the search time, right, or reduction in operating multiple data points, because it gives you a sort of functional parallelism of execution. Now, having said so, these are really very good things in terms of the mathematical postulates or the physics of the system. But when we come to reality, we find that though we tell that there are a large number of states which can be represented, but these states are very fragile, which means that though we have a large number of states, but ultimately the quantum state vector, okay, can be very fragile, which means that it can generate some oscillations, and due to some oscillations, it will not go to a definite state, but it can have a sort of probabilistic distribution over the states, and this probability distribution might actually reduce the expectation value of a particular state, which is your result state, and then it will be an erroneous type of result, okay, because your algorithm leads to some probability of distribution, and due to the noise in the system, and as these states are very fragile, these states will in reality define some other distribution, and so this difference is obviously an error or noise, whatever you can tell, right? And this is phenomenal, and this amount of noise increases once we have larger qubits. So though we tell that, okay, that means quantum computer at the present point of time, okay, that means quantum computer has an immense probability of crunching a very large amount of data with smaller number of qubits. But again, increasing the qubits will actually make the system more vulnerable. That's why you will see that the increasing the qubit in a quantum system is a particular technology trend which the quantum system manufacturers are actually going into, right? IBM have scaled up the qubits to 127 qubits in each of the quantum processing units, and using a distributed quantum processing with a very strong connectivity between all these QPUs, they are able to generate 1,000 qubits, 1,000 qubit type of computing. Okay, but still we are at the era of NISQ era, which means a noisy intermediate state computing. You can tell that, sir, there are error correcting techniques which are pretty available, and we know that in classical computing also, in many of the critical critical infrastructure, in many of the critical infrastructure, we see that, okay, we see that these error correcting codes, first of all, the the detection of errors and then correction of errors through efficient coding techniques are being done. Now this is also there in quantum computing, right? Quantum error correcting codes is also very, very popular. But the challenge is that this error correcting codes requires a lot of redundant qubits, okay, excess qubits, okay, and these excess qubits are not possible at this point of time because we have less number of qubits in the system itself. So nobody has the luxury to employ, okay, 7 or 9 redundant qubits for each qubit which is for your application data. So that's why in the limited qubit, we are at the era of NISQ, noisy intermediate state quantum computing, not the fully error resilient fault tolerant quantum computing. But FTQC or fault tolerant quantum computing is very likely to come in the next 3 to 4 years. Okay, because the progress of quantum computers is such that it will very soon hit the 5,000 qubits, okay, benchmark, 5,000 qubits, okay, line. And once we reach the 5,000 qubits, once we attain a quantum system having 5,000 qubits, obviously we are going to the era, okay, where we can tell that, okay, hey, this is here now we can go for fault tolerant quantum computing. Okay, so still error resilience and error rates are pretty high, and right, many of the techniques are now being worked out that what we can do in NISQ, right, and then also thinking over that what we can do in the FTQC era when we have large number of qubits. Okay, and suitability is something which means that, suppose we have quantum computers, right, it is not that all the algorithms just at a straight go can actually get executed here. Okay, so we have to find the quantumness of the algorithms, and that is suitability. Okay, so now this is what is a simple quantum state, right? If you see this, okay, let me use a pointer here. Yeah. Okay, so if you see this vector, okay, and if you see this particular sphere, this is called a Bloch sphere. This is a 3-dimensional sphere having 3 axes. Okay, this is the x, this is the y, this is the z axis. Okay, two specific values has been given here. One at the top of the z-axis, which is called the 0 ket, and this particular sign is used to just tell that, hey, this 0 is a quantum state, not a logic 0. Okay, so there's a little difference between logic 0 in a classical computer and a quantum state 0 in the quantum computer. So this is a 0 ket, which is across the z-axis, top of the z-axis, and this is the 1 ket, which is the bottom of the z-axis, right? But z-axis is not only the axis. Those z-axis is the most common axis, okay, where we represent the vector, but it is not only the axis. Okay, there are 2 axes, x and y, and if you look into this particular generalized representation of the vector psi, which is a vector which starts from the origin of the sphere and touches the surface of the Bloch sphere. Okay, and the Bloch sphere is a unit radius sphere. So the ultimate dimension of any vector here is ultimately 1. But if we try to generalize it, this particular vector is generalized by 2 angles. One is its angle with the z-axis, and another one is its projection on the xy plane and the axis it makes with the x-axis. So this is called the phi, and this is called the theta. So the position of the vector psi at any point on the surface of the sphere can be well defined by 2 parameters. One is called the theta and one is called the phi. Okay, I think it's fine. So this theta defines the complex amplitude associated with the generalized state. Okay, that if I am working on the z basis, the 2 basis states are 0 and 1, and so the theta, the value of the theta defines the amplitude. Okay, that means for the 0, right, and similarly defines the amplitude for the 1. Okay, and this phi actually defines the phase of this particular state. Okay, so theta and phi, the 2 parameters, and now we see in this example that, the different values of theta and phi can lead to different orientations of this vector. In fact, if we make this theta equals to pi by 2 and phi equals to 0, you can obviously find that this psi is just the x-axis, okay? Right? And if we make it a little bit different, pi by 2 and pi, this psi is just the opposite direction of the x-negative axis. So these are the things what you do. And if we make pi by 2 equals to theta equals to pi by 2 and phi pi by 2, you actually touch the y-axis. Or okay, and in the other case, you touch the negative of the y-axis. So these are the easy ways by which you can just move the vectors, and you can. What is the crux here? The crux here is that if you move the vector all around by changing the values of theta and phi, and you try to do measurement across the z, x, or y, right, you will get different values of the measurement based on how you have oriented your vector. Okay, so a quantum operation or a state transformation, maybe hey, you start the vector at some orientation of theta and phi, and then as per your requirement, what you want to measure across x, y, and z, though the most common measurement axes are z-axis and x-axis. Okay, we hardly measure across y. Okay, so but we can do that, right? So it means that means the orientation of this quantum state vector and the choice of your measurement axis gives you the value what we obtain from the update of the quantum state. Okay, and this is so interesting in quantum, and this you can do by applying the quantum quantum operations or quantum logic gates. So now I come to the quantum logic gates. So these quantum logic gates are nothing but they are single qubit gates. Here I define all the single qubit gates, and these single qubit gates are commonly called as poly gates. Poly gates, okay, these are the gates which actually move you across x, y, and z directions. Okay, poly x, poly y, and poly z. The poly x is basically a pi rotation across x-axis, and this is actually a NOT operation. Okay, so because if we define pi, you can easily see that if we define pi, we come from 0 to 1, which is a NOT operation, 0 to 1, and if we go in another direction, it will be 1 to 0. So pi rotation across the x-axis will change from 0 to 1 and 1 to 0 if we measure across the z-axis, right? And there is a typical case called Hadamard, which can take any value on the z-axis and can place it across x positive or x negative. Okay, depending on whether we start from 0. If we start from 0, it will place it across the x positive. If the vector starts from this orientation 1, it will place it across the x negative, right? And so these two states, x positive and x negatives, are equally superposed states across the z basis. Okay, so these are so interesting things. And when we look into this particular transformation operations, they are matrix operations, they are unitary matrix operations, and their dimension is 2 to the power n plus 2 to the power n, which means that if I am working on a single qubit, the matrix dimension will be 2 cross 2. If I'm working on 2 qubits, the matrix dimension will be 4 cross 4, and then onwards. Okay, so these are the generalized representations of the different matrices. Only the thing is that these matrices are unitary matrices, which means that all the coefficients of the matrices are in general complex, right? And also they are complex. And also, if I represent a matrix by representation of U, unitary matrix U, then due to its unitary matrix, I can always find an inverse of the matrix. And the inverse of the matrix U is nothing but the conjugate transpose of this matrix. So what you do, you have a matrix U, and you can easily generate a matrix U dagger. U dagger is nothing but take the conjugate coefficients of the matrix and then do a transpose of the matrix, and what you get an U dagger. And U dagger is nothing but the inverse of the matrix U. So which means that you can always get a matrix U inverse if you have computed with a matrix U. And this leads to another rule, which is not explicitly said in my lecture. It's called a reversible computing. Okay, that means you can always uncompute with an inverse operation what you have computed okay, with the operation of U. So you can always find an U inverse, right? And if U inverse works on the state computed by U, it will be equivalent to U inverse dot U, which is nothing but I. So the state remains same. Okay, you can uncompute the state once again. Okay, so these are the very, very good things, and these are the ways how we can look into the different types of basis states, as I said. So the basis states are across Z, basis states are across X, and basis states are across Y, right? And it depends on your choice of measurement that, oh, okay, here the vector is here, of whether we measure it across the Z axis, or we measure it across the X axis, or we measure it across the Y axis. Having said so, mostly most of the algorithms does it measures across Z, and in some of the cases it measures across X. Okay. Now I go to the two important phenomena I try to describe in a very short scope, which is the first phenomenon is the superposition, and the next is the entanglement. So what is superposition? You can look into this expression, okay, which tells a superposition of n qubits. A superposition of n qubits can generate 2 to the power n basis states. This is always I said, right? If you have 2 qubits, you can generate 4 basis states. Okay, so n qubit quantum system is represented as 2 to the power n basis state expansion, and each of the basis states will have their own amplitude, and the square of them is the probability of measuring the particular state in this particular basis. Okay, and obviously the constraint is that the square and the sum of all this coefficient will be 2, 1. Now I show one example, having understood that we can have n qubits can represent a 2 to the power n data points, having each of them having their own coefficients, which are the data. We can scale down to, for the example, a little bit smaller system, and in this smaller system, which we show that it's a 2 qubit system. So a 2 qubit system will have 4 basis states, 0, 0, 0, 1, 1, 0, 1, 1. And this is a simple example where we can show that, hey, this particular qubit representation of 2 qubit representation can be very well decomposed into 2 single qubit states. And that is possible because 2 single qubit states, right? Okay, do the tensor operation. This is a tensor operation because it's a vector space, right? Each of these are independent vectors, and their combination is a tensor operation, which leads to a 2-dimensional. That means a 4 basis state space. Okay, and this is doable. So you can decompose this into this. So superposed states can always be designed or defined in terms of independent qubit states. But if we look into this particular state, which is also a 2 qubit state because it has basis states 0, 0, and 1, 1, which are only possible if we have a 2 qubit state. But this particular state is not decomposable, or we can't decompose this into 2 independent qubit states. And so this is a special distribution in the quantum system, which are called entangled distribution. And this entangled distribution means that these qubits are very closely coupled, and you cannot disassociate the 2 qubits with one another, because you cannot represent this particular qubit system, with 2 independent qubit systems. And that is called very strongly coupled or entangled qubit states. Okay, it has many applications in algorithms as well as communications. Okay, now I look into the basic repository. What we have corresponding to the classical quantums, we have bits, qubits, and gates. In the quantum, we have the single qubit gates, which are already shown, Rx, Ry, Rz, and these are the entangled gates, which can also work across X, across Y, across Z. Okay, so they're presented like this, and what we can do, we can actually, all these transformations, what they're actually doing, single qubit transformations, what they're actually doing, they're actually moving the vector. Okay, so now suppose we had the initial state of the vector was 0, and suppose we have used a rotation gate right across the X, and it has moved it somewhere here, right? And then if we try to measure this state, obviously now if we measure the state here, we will get a 1 value for the 0, means it only records 0. There is no value for 1. There is no probability for 1. But if I measure the vector here, now after the rotation of the vector by the rotation gate, okay, I made the vector here, and now if I try to measure, I will have a probability of getting it across the zero value, or there is also a probability of getting it across the one value. So this is what I do. This is what I do in changing the data corresponding to the qubit. Okay, by changing the qubit state, right, in terms of rotation angles, I can obviously update the data which we can record or which we can get out of this qubit system. Okay, right, and this we can do, and this we can play across all the axes x, y, and z. Okay, single qubit operations. Okay, and this gives different type of distributions. Okay, disjoint distributions. I will come to distributions pretty soon when I go to machine learning. And we can generate different distributions, not only equal superposed distributions. It depends at what point we start, right? Instead of starting from a instead of starting from a 0 point, if we start the vector from here and if we apply some rotation gate, right, there is a bias, and we will change the distribution. We will change it to some distribution which is okay. That means probability of 0 is higher and probability of 1 is higher, 1 is lower, or vice versa. So we can play with single qubit distributions depending on how we move the qubit vector all around. Okay, right, and this is where we look into these circuits of the quantum circuits. And if you look into the quantum circuit, this is a Qiskit, simple Qiskit figure. Okay, right, you will see that what we have in a quantum circuits are the quantum qubits, which are represented as Q. There are classical stores which are represented as CR, and these are the quantum gates, right? And after doing quantum operations, we measured them, right? You see that this is a measurement across Z, so it's called the CRZ, and this is a measurement across X. So this qubit is measured across the Z basis, and this qubit is measured across the X basis, right? And whatever measurement value we get, that we store in the classical register, right? And this is what is the entire game of the quantum computing. Now only the way we try to perform this game is that, hey, you have to define a quantum gate in such a way that the way I start the states, the qubit states, right, and way I end it up through measurement, these states will be very favorable, where I can get the measured value as required. And to do that, you actually do this transformation using the quantum gates, so that it can suitably move these quantum vectors in a way such that after measurement I will get the value what is expected out of the system. Okay, and that is the quantum algorithm. Now we can leave this part of the circuit. This part of the circuit is only in special cases where we can further use the classical control to actually operate on qubit states, but this is not there for all technologies. Only a few quantum technologies support this, that you can again use a classical control to move a qubit state. But we can leave it for our discussion at present. Okay. Now I come to the domain of quantum machine learning, okay, which is obviously the core discussion. I think you have understood that how we can play across the distributions using the quantum vectors, orientation of quantum vectors, and that obviously gives us a lot of scope to actually exploit it in machine learning. Machine learning, in a very broad sense, is nothing but understanding distributions. Okay, so what we do in machine learning is basically we try to understand a distribution by going through its samples, right, and try to predict for the other samples, okay, when I push them, okay, to my model, which already knows the distribution of this particular, okay, right, of this particular domain, and then it can, right, and then it can either then can infer about the new sample, which is also part of the distribution. Okay, so and the inference can be a classification inference or can be a prediction inference. Okay, so this is very important in the domain of understanding machine learning. So any system which can understand distribution well, fast, right, it can be a very good way to implement our machine learning algorithms. I will come to this again pretty soon. Okay, right? And if you look into this particular figure, okay, where we have the two axes, one is the algorithm axis and one is the data axis. Obviously, CC is where we presently do the classical computing, classical data classical computing. But when we come to quantum computing, the present scenario is mostly CQ, means classical data, and we encode it and we generate and we push it to the quantum computing to do some sort of to get okay some sort of expedite computation. Okay, QC is still very rare, but we still do it. The simulating quantum physics in classical computer is QC. Okay, but QQ is also very upcoming. We are having now quantum sensing. Quantum sensing is something that which is inherently the quantum state or quantum information of the system, and this quantum information of a system reveals lot many things which a classical sensor cannot do. So the quantum sensors, the quantum sensing can reveal very minute change and minute fluctuations in the state, right? And if we use that as a data and a quantum machine as a computing, then obviously what we avail is a QQ. So CQ and QQ, CQ and then QQ are the most two happening things what we discussed in the quantum machine learning. Okay, and this quantum machine learning is basically a particular. So if we see these circuits related by alpha and beta, what is alpha and beta? The alpha and beta can be very simply taken as that. Hey, these are nothing but the sort, but the parameters of your gates, which are essentially doing a movement or rotation across the different measurement bases, right? Different bases, different axes, right? And if we can properly orient the vector, right, and we can choose the proper angular movement of these vectors and right, and the gets as a parameterized function of these angles, then probably we are leading to some sort of learning parameters, the parameters what we need to learn and we need to set for these particular gates so that they can lead to a least error in the measurement, right? And this is what is quantum machine learning. So we have to generate a distributions which leads to the answer, and to generate those distributions from multi-qubit states, we have to operate single qubit and multi-qubit operations, which are changing the distributions, and the parameters of these gates will be the particular learning parameters for the model so that it can generate the distribution which is expected. Okay, and for that you have to reduce the particular error of your required distribution and the distribution what the quantum model generates in each iteration of learning. Okay, and then we see that how distributions can affect. Yeah, we can generate very regular distributions using bipartite quantum states. Like if we have a very two quantum qubits, two qubits which are well separated, but they are both in a superposed states. Okay, their combination can generate an equal superposition of four states, all at 25% probability. But if we entangle this, okay, from a no entangle to a maximum entangled, we can generate different distributions. This is for four states, and this can be expanded. This can be for 8 states if we take 3 qubits. So this tweaking of distribution gives us a very clear idea that, hey, can we generate classifiers out of these quantum machines? Okay, because classifiers are again distributions. Okay, you take the samples and you distribute the samples in buckets, right? And each bucket is your class level. So can we map a classifier? Can we generate a classifier in that particular sense of distribution? And can we generate that distribution using the quantum circuits, using the choice of quantum circuits? Okay, so that is the motivation what we try to do in the quantum machine learning, right? So I just move into a little bit of this. So these are the circuits which are parameterized. So now I define the circuits in the form of parameters, right? These are the angles, right, of the single qubit operations and multi-qubit operations, right, and entanglement using those right, can generate different distributions, right, which will map okay, my requirement. Okay. So what we evolve is that what we evolve from the, so when I started the research in 2005 in Indian Statistical Institute, right, under the supervision of Professor Shishmita Shukole, right, we were here. We were mostly discussing of the circuits which are already very well defined. There is no parameter. Only the size of the circuit expands with the data size. Uh, but where we are now, at the present point of time, the quantum optimization and quantum machine learning, we are defining circuits which are u theta, and the value of theta will be some sort of training parameter what we need to adjust for the circuits, and we can take the input distribution and we can generate an output distribution as per the choice, which is favorable for our classifier or our predictor, right? And for that we have to train the circuit in terms of the theta parameters. Okay. So now I will go to the more or less the last part of the machine learning thing, that hey, how we can do this, how we can encode a classical data into the quantum model. Okay. So if you look into the data in the classical space, we also map the data into the feature space, okay, with some sort of x, and we map it to, okay, using some sort of parameter, we map it to a particular point in a feature space. We also tell that a feature transformation, right, and then using a kernel, we try to measure the feature space. Kernel is nothing but estimate each of the samples in the feature space and give a decision to that particular sample, whether the sample gives high or low corresponding to that particular kernel feature. Okay. So similarly, what we try to do in the quantum computing is also that, hey, we have to do some sort of encoding, because the data is classical. It cannot be pushed to the quantum system like that. You have to encode it, and you represent the classical data in terms of qubit. Once we have done that, we have to do some sort of feature analysis or feature kernel, which will try to map this particular, each of the data points to a particular measurement, which is as per the requirement, as per the decision, which is already being provided by your training set. Okay. So this is a very simple example. Okay. So the simple example tells you that, hey, I have a data which is of k dimensions, and how I encode it in terms of qubits. Okay. So a vector, so a x is a vector of k dimensions. Okay. So now the most easiest thing is called the basis encoding. What I do, I actually try to expand this. Okay, we try to expand each of these in terms of binary patterns. Okay, so x1 binary pattern, x2 binary pattern. For example, I give this example. Suppose x is a two-dimensional vector having values 1 and 3. So I represent 1 with a binary expansion of 0, 1, and I represent 3 with a binary expansion of 1, 1. And so the entire x will now be represented by a data which is 0, 1, 1, 1, concatenation of 0, 1, and 1, 1. So x qubit, x when I represent it with qubit, it will take 4 qubits, which will be initialized with value 0, 1, 1, 1 respectively. And this is how we pass this x qubit to an equivalent quantum information. But this is not so good technique, because suppose x is of k dimension, right, and each of the value require p bits to encode in the binary string. So you require x cross p qubits, okay, to represent this particular vector, okay, in the quantum. So it's a huge cost associated with the quantum system. Okay. Okay. The other way of doing this is that, hey, we try to normalize it and try to expand this on the basis. So we have again the k dimension vector, but this k dimension vector is normalized so that all the coefficients are, that is, sum squared to 1. So what we can do, we can now for each coefficient of this particular each of the features, we can associate each feature with a particular basis. So this dimension vector will be represented by a superposition of the qubits on a basis, and what we can do, we can represent a k-dimension vector with log k basis states, log k qubits, sorry, k-dimension vector with log k qubits, right? And this vector can be expanded in the basis states, right? Using k basis states, okay, using log k basis states, we can generate k basis states, right? And the coefficient of each basis state will be corresponding to the feature value of each of these particular features. Okay, so k features encoded by log k qubits, and the amplitude and normalized, okay, and the amplitude of each of the bases will be corresponding to the corresponding feature value. And this is also one of the way we can do it. Okay, amplitudes, we can we can encode the state in amplitudes of the bases. Okay, and the most useful one is called the angle encoding. Okay, what we do in angle encoding is that we have already seen that obviously we can associate rotation with each qubit state. Now what do? We try to give this particular values of this, but x1, x2, xk as a rotational parameter of the qubits, right? And the rotational parameters can vary from 0 to 360, okay, for each of the qubits, because that is the angular spread we can have. And so we can have a large number of data sets, data variations, okay, in this particular spread of angular spread. And we can just convert this x1, x2, xk into corresponding qubits by passing them as arguments of the rotation operations, okay, applied on the qubits, right? And this angle encoding sometimes sells, because as we know that angle encoding generates a nonlinearity. So what it does, it can also play a kernel trick, which means that a nonlinear distribution in the feature space will be mapped to a linear distribution due to this nonlinear transformation done by the rotation gates. Okay, and so these are the things what we do. So this is the ultimate model. We have encoded it, and then we need to perform a kernel operation which actually enhances the measurement corresponding to the classifier or predictor as required based on your training data. Okay, and I'm not discussing much on this due to limitation of time. I'm almost closing the lecture here. So this decomposition of the value of the r and theta, okay, can be again done with a synthesis technique, okay, called ANSYS, and we can decompose these gates into different ways, right? Longitudinal, vertical, hybrid, and these decomposition techniques are very standard, right? And it is also a particular thing that here this decomposition is not unique, right? You can define, because when we define u theta, it's a larger gate, but when we try to implement it in terms of the actual implementable gates, they are single qubit and 2 qubit gates. So when we try to synthesize the larger u theta function with a single qubit, 2 qubit gates, you can follow different decomposition techniques called ANSYS. And these ANSYS might not be unique, but you have to find the ANSYS which gives you the solution and which you can reach within optimal time, right? That is the synthesis cost to have for that particular quantum problem. Okay, and right, and obviously the last state is the measurement. So once we prepare the encoded form, then we use a quantum kernel, and then you have to work with the quantum kernel very well on the measurement. And measurement is something called an expectation value. So suppose you have a binary classifier. In a binary classifier, you have 2 class labels, because each of the class label defines a basis and the measurement. So now for a given particular sample, right, you need to make it to level 1 or you make it to level 0. So if you have to make it to level 1 for that particular measurement, you have to get that basis state high in the measurement, or vice versa. If you want to make it 1, right, you have to make the particular basis state corresponding to 1 very high for the measurement of the sample. So this way you actually take the training set, look into the class labels. K class labels can be defined in terms of log k qubits, right? And you can generate the distribution corresponding to each sample, which corresponds to your class level, right? And you can take the samples in a superposed way, and you can map the samples in the output distribution in the way how the class labels are defined in your training data. But though I'm telling that it is so easy, it's not so easy, because you have to, that after encoding, you have to map your kernel U theta function of the quantum circuit so that it gives you the favorable distribution, what is being defined at the training set, right? And to measure the distribution, what you need to do, you need to have the expectation value of a given quantum state for a particular basis, right? And this is the way how we calculate it, okay? Right? And to optimize this, we require classical computer, right? Because you have to optimize this in the training time. So in the training time, you can use a classical resource. So we know that hybrid classical quantum algorithms are now very ongoing. So we can use an HPC, or we can use a strong computer to actually work on the various thetas, right? And optimize it, and then settle it down. And then the quantum computer circuit is ready to go for any of the runtime samples. Okay, so these are the ways we will try to work out. Okay, so I will try to summarize this, that this is what is quantum machine learning. Okay, in the classical machine learning, you actually come from X to the kernel, okay, to the kernel, use the kernel to map it into the, right, into the decision space, right, and which is called generating the class boundary. In the quantum, you first encode it into the quantum, into the Hilbert space, which is the quantum vector space, right, and then you try to use a sort of a kernel operation which actually okay, maps it to the measurement space, and in the measurement space you have a distribution, and that distribution should be well defined, well mapped with the training set distribution. If you can do it, you are done. Okay, and so we tell different type of theta parameters in the quantum processing of the circuit, and obviously measurement. Now this is pretty good. This is almost like a convolution neural network where the feature space generation and the inference engine works hand to hand. Similarly, in the quantum also, okay, the kernel function, which actually extracts from the feature space and maps it to the measurement space, and the measurement operation, which actually tries to see whether the expectation value is as per the training set or not, they work in very closely. So there is always a feedback from the measurement, which is an error, to this particular space of the kernel, right? And we can do it very well, similarly as we do it in the case of the deep networks. Okay, so in the sense that deep networks can also be very well implemented. I'm not getting into this lecture, it's a paucity of time. Maybe some other lecture I will tell you that how this philosophy can be generated, right? And I think that's all. And these are some of the very good use cases how we can handle this large amount of data, right? Okay, this is a good work which has been very recently found in this IEEE access, where they have shown a large amount of spectral data. Spectral data consists of different features in different spectrum levels, right? It takes a lot of features, right? A different spectrum give different features, and you can due to the large amount of data, it's very difficult to multispectral image to compute in many of the classical scenarios. But in quantum, you can do that. You can represent a larger amount of data using a smaller qubit space, and you can generate some kernels which can lead to the decisions. Okay. So, and this is also a use case. This is also a use case which works pretty well. Okay, pretty well for this. This is a use case which actually settles the number of channels what we use to estimate number of channels given a set of subscribers in a cognitive radio model, which is very much used in the 5G 6G communication. And this is a very challenging problem because a lot of runtime requirements are there. The channels are there. Okay, channels have different type of noise parameters, right? And the users have different types of noise required. That means noise susceptibility requirements, bandwidth requirements. So this paper has also shown that that hey, with a smaller number of circuits, you can cater the requirement of good number of users, good number of channels, and how the length and breadth of the quantum circuits gets enhances with the increase in the number of channels, right? Only the thing I didn't mention is that in the quantum circuit, when I look into the quantum circuit, just remember that when I go into the along the x-axis, it's not the space. Okay, in the classical circuits, it's a signal flow graph, where it means that the signal flows from logic gate 1, output of logic gate 1 goes to output of logic gate 2, input of logic gate 2, and these are signal flows. But in the case of quantum, this is different. In the case of quantum, it is a temporal circuit. So it means that we start from the qubit registers, initialized at a particular point of time, 0 point of time. Then we apply a set of quantum operations in the next interval of time. Then we apply a set of quantum operations in the next interval of time, and we go on and go on. Okay. So it means that this particular quantum operation is temporal. Okay, it is the evolution of the same quantum register over the time, which is basically following the Hamiltonian principle of quantum physics. Though in Hamiltonian quantum physics, it's a continuous time evolution of the quantum state, vis-a-vis in the case of the gate quantum circuit, it's a discrete time evolution of the quantum space what we are doing, but it is actually following the same Hamiltonian. Okay, so I think that I will, and the last part. So there are a lot of things which are there. You can go through this, and this is a QTAC, which is a quantum software consortium, right? Which consists of very quantum application development. Quantum application development organizations, like we have Siemens, we have Qualcomm, we have Intel, we have Microsoft, we have TCS, right? All these have formed a consortium called QTAC, right? And get quantum technologies and applications, right, in computing. And you see there are verticals: material science, material science, engineering design, production logistics, post-quantum security, right? And the different industries, there are different business impacts, and these are different problem domains, right? There are some problems from simulation, optimization, cryptography, machine learning, right? Working across the verticals. And this is a good research roadmap for anyone who wants to start, either wants to develop algorithms for business applications, or can do theoretical application, theoretical quantum computing. A lot of problem space has been explored, and a lot of problem domains are existing in this particular space. Okay, so I end up here. I will not go, and these are the challenges. As I said, that the noisy quantum hardware is still there, right? We don't have enough amount of qubits to handle this, so we have to limit our size of the quantum circuits, and we only can go with the small scale circuits and the proof of concepts. Okay. And it also goes limited qubit availability. Quantum gate depth means the number of quantum operations you can do over a period of time. That is also limited, because as the quantum states are fragile, we cannot hold the quantum state for long. So the number of quantum operations you need to do on a quantum register is limited with time. So we can only operate on smaller depth circuits. Though in simulation we can do much longer depth circuits, but this is only in the reality. In the physical quantum devices, we can only still do the less quantum depth. Quantum gate depth means the number of quantum transitions or quantum operations you can do over the time. Okay, right? And complexity of the quantum programming is still high. So we need to train the manpower. People are not trained in the quantum programming. So there are good platforms like Quantum Qiskit from IBM, CUDA Quantum from NVIDIA, Bracket from Amazon, QSARC from Microsoft, QSIM from SIDAC, indigenously developed. So these are all platforms are there, right? And many more, Peninel, Rigetti, many more are there. But obviously, we need to train a huge amount of manpower. And obviously, my advocacy will be to start the quantum computing courses all across the institutes, right? And so that our future generation gets well trained, because we will require a huge amount of quantum programmers in the next few years to come. Okay. And the hybrid model of integration, as I said, is very important. It's not that only quantum will stay. It will be always a classical, like the parallel computers. You have a main thread, and then it goes to the GPUs, and then it again synchronizes and comes back. So this type of synchronization between the classical thread and the quantum, will be done, and we will be doing the business platforms for this. We have a lot of work going on the quantum business development life cycle. We are working with my IBM on this particular operations, of these particular activities. Okay, right. And algorithm suitability is also one of the things where the quantum engineers, quantum researchers should have a very good conceptual and hands-on on the algorithm and the quantum part of it, so that they can really analyze the quantum algorithms, and they can find that what is the best how we can get, and how we can apply these quantum algorithms, right, and how we can get the supremacy out of it. Okay, so I think I will just finish it here. So this is the these are the work what we do. We do algorithms in University of Calcutta, algorithms, circuits, error corrections, quantum business platforms. I will just skip this a bit. We are the first group in our country to get the IBM Quantum Researcher Access Award to research applications. Right, others have done it, but they are only for the delivering the quantum courses. But we are the first group in India from University of Calcutta. We've achieved this for research access award for our quantum ant algorithm, which was published in 2021. Okay, and we do a lot of things. I'm not getting into this. A lot of journal publications, IEEE, SCM transactions, quantum physics review, all we have done. Okay, and this is the important part. We are doing it, the quantum development life cycle. Now we have joined with IBM and developing the quantum business platform. We are also working with that means with HCL Technologies to do a lot of this R&D work in quantum cryptography, quantum software development, and quantum business applications. Right, and we have a very good graduates which have passed out. Right, Mrityunjay, Amit, and Shaikat. Right, Amit has already passed out. Right, and Mrityunjay and Shaikat are just finishing their PhD. Nivedita is working with PwC, working with group, and Ajanta is now a postdoc. And Shahan is a very promising student in UGCSE in our university, and he's also now the director of our startup called Choudhury Labs, which is started by our lab members. Right, these are the areas what we do. Anyone interested, any student, any researchers in this particular participation, okay, can connect us. Right, if they're interested in quantum CAD, quantum algorithms, machine learning, and cryptography. And we have good collaborations, right, in industry and academia, right, and we are still learning, and we need to. That means we think that we require people to drive this quantum algorithms, quantum machine learning, quantum systems in India. So I end up here, right, and these are the Choudhury Labs. Okay, these are the good references you can take for quantum machine learning. Okay, our publications, you can all have it. I will pass the PPT to the organizers, right? And thank you all for listening. And if you have any questions, I will be very happy to answer. Yeah.
Thank you, sir. Thank you, sir. Yes, if anyone has any question, you may ask.
Hello, sir. Am I audible properly?
Yeah, sure. Yeah.
Sir, first of all, thank you for the nice knowledge delivery session. And my question is, what is the difference between PQC and ANSARs?
Okay, PQC is ANSAR is a part of this parameterized quantum circuit. So once we have a parameterized quantum circuit, we define the learning parameter. Which is theta. Okay, that comes with optimization. But once we get that, okay, this is a large U theta, right? How we decompose it into terms of the primitive quantum operations, right? And this times you can say you can decompose it and you can generate. So this is a chicken and egg problem. So whether the optimization of the more circuits having, right, the smaller circuits having their theta values is easier, or it is better to have a larger matrix, okay, having the various theta values, right? Because the theta values are nothing but the e to the power I theta component on the matrix coefficients, right? And whether so if you have smaller matrices, then the number of thetas reduced for each matrix is small. But if you have a larger U theta, okay, right, you have a okay, that means you have a smaller. Okay, so it depends on that means what size you can have. So much more theta values will be there when we make a larger matrix, and small theta values will be there when we have a smaller matrix. But again, the numbers in the smaller circuits are more, and the number of matrices are more in the smaller circuits, right? And if you have a larger, if you have a single matrix, right, you have the matrix is single matrix is only one matrix you have to optimize. Okay, but but decomposition ultimately you have to do from the U theta, from the PQC, larger U theta, you have to ultimately decompose it into smaller gates, because ultimately you have to implement it into the quantum system. And quantum system only still now supports single qubit and 2 qubit operations. So ultimately you have to go to the answers and decompose it into very small single and 2 qubit operations. Okay. Yeah.
Okay, sir. Sir, I have another question that from PQC architectural point of view, what is the basic difference between binary and multi-class classification from PQC architectural point of view?
Okay, I got it. Yeah, yeah. So multi-class classification, as I said, it is right. The distribution is larger. Okay, so you have more class levels. Okay, so you have to have more basis states in the measurement in a multi-class classification. And in the binary class classification, you can only have two basis states in measurement. One basis state gives you the zero value, and one basis state gives you the one value. Okay, and you have to map each of the samples to higher probabilities of any of the basis states in the case of binary classification, depending on your training set. And in the multi-class classification, you have more basis states because your class levels are more, right? And you have to map each samples, and probability of each samples will be more across that means you have to have a larger qubit distribution. Okay, right, and you have to make your sample to fall high in one of the basis states and fall low in all the other basis states. Okay, so in the
So, sir,
case of
how can we distinguish from any this difference we can observe from PQC architectural point of view
this is a
in
good
any
question.
general
Yes, so
difference?
yeah. Yeah, so PQC architecture will lead you to, that means you have to think on the measurement, right? You have to think that what are the basis states on across which I have to measure, right? And your U theta, training of U theta should be done in the iterations, so that the measurements what you do across the basis states, okay, map with your training data, right? In the sense, what it means that means if you are trying to match with more number of basis states, the distribution, right? Obviously, distribution is larger distribution, so it's it's a variation, right, in terms of the standard deviation. Okay, standard deviation will be more compared to a smaller distribution. Okay, so that is the extra effort obviously you have to take once we move from a smaller class levels to larger class levels in the case of your parameters quantum circuits.
Okay, thank you, sir.
Okay, sir, there is a question posted by Jeet Banerjee, which says that which are the fundamental courses that an undergraduate student must undergo as a prerequisite for quantum computing, like
Yes, I
frequency.
think, I think obviously that means a course on quantum physics will help you. But quantum physics, the quantum physics in a sense of a deep dive in physics is not required in that sense. Only some of the theories like measurement operations and bracket notations, right, and the quantum state space, this will be good to have a go. But the most important is the mathematical concepts. Okay, so mathematical concepts in terms of the vector space, right? Obviously, Fourier helps you because ultimately when we go into the complex domain, right, your distribution in the complex domain can be well analyzed using the Fourier sampling. Okay, right, right, and obviously the vector space, probability, right? I think these are the things you have to know first, and then obviously information theory and cryptography are the application domain where you can use quantum computing. Okay, yes.
He also continued that are there any application of quantum computing in healthcare?
Yes, so it's very good. Yeah, so there are a lot of applications are coming up, right, in the small scale, due to because we cannot still meet the requirement of the full scale applications which can solve the real business. But a lot of applications have been come up for healthcare. Recently, one application has been developed by IBM with jointly with IIT Madras. Right. You can connect me, mail me. I will try to get this to you. Okay, that this is something. Okay, this is something. Okay, I will. Okay, happening because a lot of data crunching can be done in medical, right, and it's also useful parameter. So most of the in the global research, most of the applications in the finance, space science, health, drug discovery, material science have been taken care by quantum computing. Quantum algorithms and proof of concepts have already been done. Some medium scale algorithms are also being running in different industries. Okay, logistics is also one of the important applications. So deploy quantum algorithms. There are physical machines now. A lot of physical machines have come up. IBM is there, right? Rigetti is there, Cold Quanta is there, okay, IonQ is there, right? And many of the universities have their own systems, physical quantum systems. India is trying to build physical quantum computers, and I hope within 2 to 3 years it will be coming up. Okay, I'm not disclosing how it is being done, right, and who all will be doing it, but TIFR has a small qubit system. Uh, okay, so IIT Chennai is also trying to build one. ISC Bangalore is also trying to build one. Okay, yeah.
And one last question from Kinko Adhikari. Where to deploy these quantum algorithms in real life hardware?
Yeah, so this will be the cloud infrastructure. So this will be cloud accelerators, quantum cloud accelerators. So you need to have a to and fro movement between your applications and your quantum cloud, right? And this quantum cloud will obviously will accelerate your algorithms to the quantum engines, okay, and you will get the fruit out of it. Yeah.
Okay,
Like
thank you, sir.
commercially you can use the presently commercially available IBM cloud you can use. Amazon also gives commercially available quantum cloud. Yes.
Okay, thank you, sir. So to this we come to the end of our session. Once again,
Yeah, I have one question.
Okay.
Yeah,
Yeah,
sorry,
yeah.
sorry.
Yeah,
Please,
Devarshi,
please.
please.
Yeah,
Please.
so yeah, sorry for the interruption. So a small quick question I have. So first of all, thank you, sir, for this very nice presentation. Sir, actually, nowadays machine learning is being used in everywhere, right? So whenever some concepts of any AI or any computer vision related applications are there, this machine learning or deep learnings are very hot topic like that. Everyone is applying everywhere. So, sir, I'd like to ask you one thing that what are the fundamental or is there any key perspectives are there which make the differentiation between this traditional machine learning and the quantum machine learning? So, is there any key points or benchmark that we need to keep in mind while applying this traditional machine learning or this quantum machine learning?
Yeah. So the machine learning in generally is basically try to see the distribution in the feature space. Feature space is very important in machine learning. It tries to see the distribution of the feature space and then try to generate, try to extract inference, okay, by applying kernel on the feature space. Okay. Now, obviously you cannot say in that way that, okay, that means, okay, one good trick is that why people are using in the material science and drug discovery, inherently the data what we have there, right, are the data which deals with the energy bonding, right, of the, okay, bonding of the atoms. Okay, now this energy bonding of the atoms can be very, very well simulated, okay, by a quantum system which we can build as a sort of equivalent, okay, to those real physical atoms, right? And then you can actually try different types of ways, okay, to maximize or minimize, okay, certain interaction probabilities, and then try to find out using the parameter updates of the quantum functions, which is also again some sort of machine learning, because you don't have any sort of mathematical function coming out of that. You know that these are the end results how I have to reach, and I have to start with this particular distribution, a distribution of energy, and we have to try to see whether after a certain sequence of operations, okay, some of the energies are maximized. So now these particular problems, which are inherently deals with the quantum parameters of the system, can very well map into the quantum simulators, and you can get a very good drive to solve those problems. So that's why you will see that a lot of quantum physics and quantum chemistry problems are very well handled in the quantum computing systems. In the case of the other types of classical problems like finance and all these things, the thumb rule is that whether you have a sort of scenario where you have a sort of the variations are pretty large, right, and you need to reduce the resource, and you need to have a reduction in the computation effort. Whether if reduction in computation effort or computation cycles is one of the target, then obviously you can look into that, hey, can we try quantum computing? But obviously you cannot say that from a given particular problem, right? You cannot say that, okay, this particular, apart that this particular problem itself is of a quantum system, a quantum mechanical system, right? It's very difficult to say at first hand that, hey, this particular algorithm has, because only the crux here is that the superposition, interference, right, and entanglement, these are the things which can give you some distributions which you cannot have in classical domain. Okay, so if you try to bifurcate the feature space, right, in some way which is very what I can say, which is very different, right, you can try quantum, because quantum can give you those type of different distributions, right? But it's very difficult at the level one to tell that, hey, this particular problem can be there. But obviously people have found that graph problems, that if you see our work, we have worked with a lot of graph problems. A lot of graph problems have a good point. They are well taken care, because why? Graph can be represented as a large number of connectivity, right? And those connectivity of data, right, can be well defined in terms of the superposed states, which are represent a basis distribution. So if you have a graph type of data, I think quantum algorithms or quantum machine learning algorithms play a very good role. Right, and the other point, as I said, that you can represent the data itself, which comes from the quantum mechanical interactions in the matter. If we can try to trap it and try to simulate it in the quantum systems, those are easy problems to solve.
Yes, thank you very much, sir, for the nice explanation. And before I just conclude, just one small request to our team, IEEE IIT Kharagpur, that if possible, kindly host sir in person in our campus. So it would be a great for like listening sir live, and also the undergraduate and graduate students will be getting much more information of it. So thank you, team, for hosting sir once again, and thank you very much.
Thank you. Take care, all of you. You should be a very successful professionals in the next future. Okay, thank you.
Sir, before I want to share one thing, last thing, that I think it's already visible. Yeah. So on behalf of IEEE SB and IIT Kharagpur, we present this virtual memento as small token of appreciation. And also, before closing, I would like to request all the participants to please turn on their cameras and microphones so that we can take a group photograph, if possible.